Hi, my name is Yuval Filmus, and today I'm going to talk to you about our STOC paper, Approximate Polymorphisms. This is joint work with Gilad Chase, Minzer, Elchanan Mossel, and Nitin Saurabh. So let me start with something you might be already familiar with. This is linearity testing. So we are given a Boolean function f. It accepts n bits as input, and it outputs a single bit. Now, suppose first that for every two inputs x and y, if we compute f of x, x or y, then we always get f of x, x or f of y. So if this happens, then we know that f is an XOR of a subset of the coordinates. Now suppose that this holds only for most x and y. Okay, now in this case, f is not going to be exactly an XOR, but it is going to be close to some XOR. This is what is usually known as linearity testing. Finally, suppose that this equation holds with non-trivial probability, meaning more than 1/2. In that case, we can say that f correlates with some XOR. Okay, so another way of stating the first bullet is saying that f is a polymorphism of XOR. In the second case, f is an approximate polymorphism of XOR. And finally, the third bullet is about what is known as the list decoding regime. So in this talk, we're going to discuss what happens when we replace XOR with some different function. Okay, so let us start with discussing exact polymorphisms. Okay, so here's the statement we considered above. F of x, x or y is equal to f of x, x or f of y for all x and y. And another way of stating this is saying that f is a polymorphism of the function g of ab, which is equal to a XOR b. Okay, so in this case, if this happens for a function f, then the function f is an XOR. Now here's another example. We replace throughout XOR by AND. So a function f which satisfies this equality here is known as a polymorphism of AND. And which functions satisfy this? So we have the AND functions, and we also have the 0 function. And we also have the 1 function, the constant 1 function, but this is like an AND of 0 variables. Finally, an example where G has more than 2 inputs. Okay, so in this case, G has 3 inputs, and it computes their XOR. Okay, so once again, we can define f being a polymorphism of G, and this is the same as this equation here. And in this case, the solutions are XORs and their negation. Okay, and now on to the general case. Okay, so this is work of Dokov and Holtzman, and they showed that if f is a polymorphism of G, then either f is a trivial polymorphism, a so-called trivial polymorphism, so either it is a constant, it is a projection or a dictator, an xi, or the negation of a projection or a dictator, also known as an anti-projection. Okay, so this is one option. If G is an XOR or its negation, then F could also be an arbitrary XOR or its negation. Its negation, it depends on some parity issues, which we won't get into. Another case is if G is an AND function of possibly more than 2 inputs, then F could be an AND. And the same with OR. So unless G is an XOR, its negation, an AND or an OR, then the only possible polymorphisms F are the trivial polymorphisms. Okay, so this is what happens in the exact case. And now let's move on to approximate polymorphisms. Okay, so here's linearity testing. We have a function f, and it satisfies that f of x, x or y is equal to f of x, x or f of y for most xy. Okay, most meaning with probability very close to 1. This is the same as saying that f is an approximate polymorphism of the XOR function. Okay, and we've seen that in that case, f has to be close to an exact polymorphism of XOR, okay, which in this case is an XOR. Here's another example, approximate polymorphisms of the AND function. Okay, this is exactly the same condition, only with XOR replaced by AND. Okay, in this case, we have a result known as AND testing, originally due to Ilan Nechama, who had a dependence on N, and to myself, Noam Lifshitz, Dor Minzer, and Elchanan Mossel, without a dependence on N. So again, in this case, f has to be close to an exact polymorphism of N, which in this case is either the N function or the constant 0. Okay, so now for the general case. So you could conjecture that if f is an approximate polymorphism of some function g, then f has to be close to an exact polymorphism of g. Okay, because this fits the cases we've seen above. Now this is true in most cases for most g, but not for all g. So here's a counterexample. Take the NAND function. Okay, so now we are going to construct an approximate polymorphism of the NAND function, which is not close to a polymorphism of the NAND function. Okay, so here's how we're going to define it. So in input x, if the input x is balanced, so this is just the Hamming weight of x, if it's balanced, then f is going to behave like an AND of the first two coordinates. And in contrast, if x is skewed towards ones, then it's going to behave like an OR. Now let's see why this makes sense. So we want to check whether this equation holds with high probability. So let's see what happens to the left-hand side. So if we choose x and y at random and compute their NAND, then the Hamming weight is going to be very close to 3/4 n. So in that case, f is going to behave like the OR of the first two coordinates. And this is what we are going to get. On the right-hand side, in contrast, f of x and f of y are going to behave like the n function because the inputs are random and so balanced. So in this case, this is what we get. And now you can see that the left-hand side and the right-hand side are equal due to De Morgan's law. Okay, so indeed, f is an approximate polymorphism of G. And according to the classification that we've seen above, actually there are no non-trivial exact polymorphisms of G. So this f is not close to an exact polymorphism of the NAND function. Okay, so this conjecture is a bit too naive, but we can correct it. Okay, so here's our first main theorem. It states that if f is an approximate polymorphism of G, then one of the following holds. So either f is close to one of the trivial polymorphisms, or G is an XOR or its negation, and f is close to an XOR or its negation, or G is an AND, and then f is close to an AND, or the same thing with OR. And now we're going to have two new cases. So if G is an AND, then f could be close to an AND. This is what we've seen in the previous slide. And the same with NOR. And in all other cases, f has to be close to one of these trivial polymorphisms. Okay, so this is our first main theorem. And now let's see how to prove this theorem. Okay, so I'm not going to actually explain the proof of the theorem because really the heart of the proof is this main lemma that states that if f is an approximate polymorphism of G, an arbitrary G, then f must be close to a junta. Actually, G cannot be arbitrary because this is false if G is an XOR or its negation. But these cases we know how to handle, so we can ignore them. And I remind you that the junta is a function which depends on a few coordinates, typically a constant number of coordinates. Okay, so assuming this main lemma, let's see how to prove the main theorem. So according to the main lemma, we can approximate f with some junta phi, which depends on k coordinates. Okay, and let's assume that these junta coordinates are the first k coordinates. And now we're going to sample x double prime and y double prime at random. And these are going to fit into the second part of the input. Okay. And now we're going to define three functions, alpha, beta, and gamma. Alpha is what happens to f when we plug in x double prime at the second place. Beta, the same thing with y double prime. Gamma, the same thing with their AND. Okay. And now notice that alpha of x prime and beta of y prime is usually equal to gamma of x prime and y prime. Okay, and here is really the trick that we're going to use here. So we're going to make sure that this error probability in this approximate is so small, okay, that actually this has to be an equality. Okay, so if the error is at most 4 to the minus k, or rather smaller than 4 to the minus k, then this has to be an equality. Okay, and in this case, we're essentially done. Why? So Dokov and Holtzman actually classified the solutions to this more general equation. Okay, so we know all the possible solutions of this, all possible alpha, beta, and gamma. And now we're done because f, we know, is close to the junta phi, and also alpha is close to the junta phi, at least on average over x double prime. Okay, so this means that f is close to alpha, and we know what alpha could be. Okay, so this is the idea of the proof. And sorry for the slight mistake here, this should be y prime rather than y double prime. Okay, now let's move on to our third and last topic. This is the list decoding regime. Okay, so above I've mentioned the list decoding regime for XOR. Okay, so we have a function f, and it satisfies this equation with probability half plus epsilon. And in that case, we can say that f correlates with some XOR. Now, we cannot make this 1/2 any smaller, because if we choose f at random, then on the one hand, this equation holds with probability very close to half. And on the other hand, f doesn't have any significant correlation with any XOR. And now we want to ask what happens if we replace XOR with a different function. Let's say the n function. Okay? So we're looking for the smallest alpha such that if we know that f of x and y is equal to f of x and f of y with probability above alpha, then f correlates with a junta. Okay, so this is very similar to what we had above. We want to find what replaces the value 1/2. Now, one thing did change. Instead of XOR, we have a junta. So you can think of a junta as a small XOR. Okay, this is roughly the same thing. Now, why did we switch from XOR to a small XOR? So this is a stronger statement, and we would like maybe to have this stronger statement for XOR as well, but this is impossible because actually there are exact polymorphisms of the XOR function which are not small XORs, which do not have any correlation with any junta. For example, the parity of all the input coordinates. But for a function like n, it is possible. Okay, so what's the best value of alpha? Here it is. It's approximately 0.814975. Okay, so this is our second main theorem. Now let's state it formally. Okay, so this is our constant alpha. Now, on the one hand, if this equation here holds with probability above alpha, then f has to correlate with a junta. On the other hand, we can find some f such that this equation holds with probability almost alpha, but f doesn't correlate with any junta. Okay, and how does this f look like? So on balanced inputs, f is just a majority function. Okay, so this is what happens when we plug in the x and the y. And if the input is skewed towards zeros, so this is what happens on the left-hand side, then f is some kind of threshold function. Okay, so I'm not going to explain why this is a good idea. You'll have to take a peek at the paper. Okay, so finally, let me very briefly mention some open questions. Okay, the first open question is to generalize our work from polymorphisms of functions to polymorphisms of predicates. Okay, I'm not going to explain what exactly is a polymorphism of a predicate, but let me just say that this would generalize two seminal results. One of them is a quantitative errors theorem due to Kalai, Keller, and Mossel, okay, in separate works. And the other one is a recent nice work of Friedgut and Regev about almost intersecting families, okay, which improves earlier work of Dino and Friedgut. Okay, so this is the first question. The second question is about larger alphabets. Okay, so far everything has been over the binary alphabet 0, 1, but what happens if the function maps 0, 1, 2 to the end to 0, 1, 2? We don't know. A very natural question is about the list decoding threshold for an arbitrary function g. Okay, so we know what happens for the XOR function. This is just list decoding in the context of linearity testing. We've seen above what happens when g is the end function. What happens for an arbitrary g? We have some initial results, but we don't really have a formula for arbitrary g. And finally, let me mention that there are some quantitative aspects of our results, which kind of we skipped over, but which there are some really serious gaps, some exponential and double exponential gaps in these quantitative aspects. So if you're interested, please take a look at the paper. So thanks a lot for listening. And that's it. Hope to see you at the talk.